speaker is Dr. Mamata Sahoo from the University of Kerala. She will be talking about transition from random self-propulsion to rotational motion in a non-Markovian microswimmer.
Good morning all. So first of all, let me thank the organizers for giving me this opportunity to be here. So I would be talking about transition from random self-propulsion to rotational motion in a non-Markovian microswimmer. So I think microswimmers are a kind of, this is active matter system. So already yesterday we have had a couple of talks based on the active Brownian dynamics or active particles. So I will not go in detail. So briefly, let me introduce the topic. So microswimmers are a class of non-equilibrium systems which are inherently driven away from equilibrium. They have the ability to self-propel by their own and they generate a spontaneous flow in the system by consuming energy from the environment. And that is the reason they are active in nature, and the dynamics governed by these swimmers are basically known as active Brownian dynamics. So in the dynamics of microswimmers, rotation plays a crucial role. Sometimes the rotation enables the microswimmers to avoid obstacles to locate food and other resources, or maybe also sometimes for the interaction in the surrounding medium and so on. But for the chiral microswimmers with shape asymmetry, the rotational trajectories are the typical feature of their dynamics. But chirality is not the only key factor for the performance of rotational trajectory. So sometimes when the microswimmers are placed in external confinement, for example, like here Hexbug is self-propelling in a parabolic disk, so they perform rotational trajectories. And Narendra Retail recently, they reported that an achiral microswimmer, they can make a transition from random self-propulsion to rotational motion in a non-Markovian environment, and that is purely induced by the presence of memory in the medium. And they did it by investigating the active Brownian particle model. But the inertia was not taken into account in this model. But inertia in the dynamics of microswimmer, in many situations, the inertia is found to have unavoidable impact. So that's why, hence, in our work, we took an interest in the dynamics of an inertial achiral microswimmer in a non-Markovian environment by considering an Ornstein-Ulmbach particle model. So this is the model in which the velocity of the particle is stochastic, and it follows Ornstein-Ulmbach process, which is basically exponentially correlated noise. So it is the noise correlation decays exponentially with a time constant Tc. So Tc is the time during which there exists a finite noise correlation in the environment or medium, and the particle self-propels in a specified direction along with making random collisions with the surrounding fluid particles. So that's why the Tc can quantify or it can be referred to as self-propulsion time or activity time of the particle. Then the non-Markovian environment can be realized by introducing a time-dependent memory kernel in the viscous drag, which in our model we have considered a exponentially time-dependent memory kernel, which decays with a time exponentially with a time constant Tc prime. And Tc prime can quantify the persistent duration of memory or memory time scale. So with this model, we have exactly solved the dynamics, and we have established from the exact solution of the dynamics, we have established a phase diagram in inertia memory parameter space separating the oscillatory behavior of motion from the non-oscillatory behavior of motion. So further, when we investigate the swimmer trajectories, we observe that in the oscillatory regime of inertia memory parameter space, the inertial achiral microswimmer, they can make a transition from random self-propulsion to rotational motion. And the orientation of the rotation can be investigated, can be computed from the instantaneous direction of the instantaneous velocity, which can be denoted by which is here denoted by the parameter theta. And in the inset, we have shown the time evolution of the orientation, and you can see that here for the typical case of rotational trajectory, the time evolution of orientation shows slanted stripes, which are consequence of rotational motion either in clockwise or counterclockwise direction. So this observation predicts that the rotational orbits reverse their orientation spontaneously, and the frequency of orientation reversal, it is found to decrease with increase in persistent duration of memory. So further, in order to characterize the rotational motion, we calculated the mean square angular displacement, and we simulated this mean square angular displacement, and we have shown here the time evolution of the mean square angular displacement, and that long time behavior is always found to be diffusive in nature, whereas the initial time regime, it is the interplay of subdiffusive behavior of motion as well as superdiffusive behavior of motion. So the subdiffusive regime is the indication of an induced transient confinement, and superdiffusive regime is the indication of breaking of this confinement or caging effect. So then from this observation we predict that maybe even if there is no external confinement in the dynamics, the swimmer performs rotational trajectories in the transient regime because of this induced transient confinement. So when we further investigated the trajectory with the duration of activity, we observed that the trajectories get suppressed with the activity time, and this suppression of trajectories is an indication of trapping of the swimmer with the persistent duration of activity. And this trapping effect was supported by the position probability distribution, which is transient position probability distribution, and which takes a Gaussian shape. And with increase in persistent duration of activity, the distribution becomes narrow, and it shows a sharp peaked structure at the center, which is a clear indication of the strong confinement with activity time. So similarly, when we increase the persistent duration of memory, then what happens? Maybe the induced confinement becomes weaker. As a result, the swimmer is found to diffuse away from the center. As a result, the probability of finding the swimmer at the center decreases. So this similar behavior was observed experimentally by active Janus particle in an acoustic trap. So further, when we investigated the swimmer trajectory in the stochastic environment by varying the noise strength, we observed that in the absence of the noise strength, then the swimmer simply oscillates along the diagonal line. And in the presence of noise, that means for a non-zero finite value of the noise state, it simply makes a random self-propulsion. Then upon choosing a suitable inertia and appropriate memory, then it performs rotational trajectories. And at this parameter space, if we further increase the strength of the noise, then the trajectory is simply get enhanced without altering the shape of the trajectories. And the frequency of direction reversal is found to remain almost constant with the strength of the noise. So from this observation, we clearly we confirm that there is even if in a stochastic environment, an inertial achiral microswimmer, they can make a transition from the random self-propulsion to rotational motion by fine-tuning the inertial timescale as well as the memory timescale of the medium. So the noise, as well as here in my model, the noise, inertia and memory plays crucial role in the performance of rotational motion. So in the absence of any one of them, the rotational motion will not occur. So with this, I would acknowledge both of my PhD student, Adarsh and Musin. Musin is already here, and the funding agencies. So thank you for your kind attention.
Questions?
I just had a small question. So you were comparing your answers with the experiments.
No, I didn't compare, but these are the
10th or 11th slide, you had something with experiments?
Yeah, I think this is the experimental observation. So they have this. I have not compared, but the qualitatively our behavior observation
so
is.
My question was just about that. Basically, the kernel you have assumed something like exponential. So I was wondering, like, because you're comparing it. So for what can you say about the experimental kernel? I mean, do you have any idea about what's the non-Markovian?
Yeah, so I think this is basically what happens here when they are increasing the confinement strength. So this is basically it is diffusing away from the center. When they are increasing the confinement strength, it is confined more. So it is just getting sharp. It is just becoming narrow. The distribution is non-Gaussian, and it is becoming. Yeah, so this is distribution is non-Gaussian and becoming narrow. So this is just the trapping kind of thing. So here qualitatively we are also observing the similar kind of behavior. So that's what I am saying, that the active particle also shows the similar feature which has been experimentally verified. So now I am not comparing with the experimental data because the model is different.
Further questions? Let us thank the speaker.